In last class, we discussed about the electrophilic substitution reactions. Today, we will discuss about one of the application of the electrophilic substitution reaction is nothing but Friedel-Crafts alkylation. Application number 3. What is the Friedel-Crafts alkylation? Conversion of benzene to alkyl benzene in presence of anhydrous Lewis acid is known as Friedel-Crafts alkylation. I will write the definition first. Conversion of benzene into alkyl benzene. In presence of anhydrous Lewis acid. Already I gave you what is the Lewis acid. Example for Lewis acid also I have given. Then, so what is the reaction? Conversion of benzene into, this is the benzene into alkyl benzene in the presence of anhydrous Lewis acid and alkyl halide. Is known as Friedel-Crafts alkylation. Here benzene on treating with alkyl halide RX, X means halogen, in the presence of anhydrous AlCl3, AlX3 I am taking, this is also Lewis acid. So what happens here? Benzene is converting into alkyl benzene. What is the byproduct? HX. How? Benzene C6H6, molecular formula of the benzene is C6H6. Every carbon is having hydrogen. Hydrogen is replaced by alkyl group. HX is eliminated. Hydrogen is replaced by alkyl group. R is connected to benzene ring. In the place of hydrogen, R group we are writing. This is alkyl benzene. Benzene. Then, how do we get that one? We can understand based on mechanism. What is the electrophile? This is the electrophilic substitution reactions. Already I discussed in last class. So, what is electrophile in this reaction? What is the importance of aluminum, anhydrous aluminum halide? So, these are all I will discuss step by step. Mechanism. Then step 1. Electrophile formation step. Then how do we get electrophile? For example, first of all, in beaker, alkyl halide we have to take. Halogen is having 3 lone pair of electrons and we are adding slowly anhydrous AlCl3 or AlX3. So Lewis acids are electron pair acceptors, electron deficient species. So it take electron pair from the halogen. Between the halogen and aluminum bond formation takes place. So what happens here? R halogen AlX3, aluminum gets negative charge, halogen gets positive charge. Remaining 2 lone pair of electrons are there because 1 lone pair is participated. Then this is unstable. Halide ion, halogen ion take electron from the alkyl group. R is becoming R plus because R has donated a pair of electrons. R gets positive charge. Aluminum is connected to 4 halogens, gets negative charge. So R plus is called alkyl carbonium ion or also called alkyl carbocation. Alkyl carbocation. This acts as electrophile. Then, so I told you here anhydrous AlCl3. What is the importance of AlCl3 and etc. We can discuss in mechanism. So in this step, what can we understand? Aluminum halide, because of aluminum halide, aluminum chloride, aluminum bromide, etc. Aluminum halide, because of that reason only, because of presence of the aluminum halide, alkyl carbocation electrophile is generating, because this is acting as catalyst, and because of aluminum halide only, alkyl carbocation electrophile will be generating. That is the importance of aluminum halide here. Then in second step, after formation of electrophile, what happens in second step? Step 2. Electrophile attacking step. Electrophile attacking step. We'll see what happens here. Benzene. Is going to react with R plus, is acting as electrophile. So whenever after formation of the R plus, we are introducing the benzene. So R plus, alkyl carbocation or alkyl carbonium ion electrophile is surrounded by this one. So benzene is acting as nucleophile, donate electrons to this. Between the benzene carbon and alkyl carbocation bond formation takes place. So this is the double bond. Here bond is there, it is shifting like this. This carbon is losing electron, that carbon gets positive charge. So remaining 2 double bonds we can represent. In mesomeric effect we have discussed about the resonance. Double bond adjacent carbon is having positive charge, resonance is possible. So double bond is shifting. This carbon gets positive charge. Double bond and R. Double bond adjacent carbon is having positive charge, one more resonance structure is possible. Double bond, it is shifting, gets positive charge, here R group. These 3 resonance structures are represented by sigma complex. These 3 are represented by sigma complex. How? So from this, what did you understand? Positive charge position is changing due to resonance. That's way. That means electrons are delocalizing by changing position of the positive charge. So we can represent as this one. So this is called sigma complex. Sigma complex is the intermediate stage of the electrophilic substitution reaction. This is intermediate. Like carbocation. Then in step 3, what happens? Product will be formed. How do we get product? Any one resonance structure we can take. Anyone, generally I am taking third one, you can see. Positive charge R is going to react with which one? AlX4 minus, which is generated in first step. Then here hydrogen is there. Then H plus will be eliminated with X minus, which is obtaining from the AlX4 minus. Then rearomaticity will be regained. This is the fast step. What about slow step? Benzene is going to react with alkyl carbonium ion, alkyl carbocation. That step is slow step. Why? Because in this case aromaticity will be destroyed. In this case it occurs very fast because it will regain aromaticity. double bond, here a double bond will be generated. Or X plus and X minus, H plus and X minus, HX, and AlX3 is there. In first step AlX3 we have taken to generate the electrophile formation, to generate electrophile. Again in last step AlX3 is generated. So that means what is the role of the AlX3 in electrophilic substitution or in Friedel-Crafts alkylation reaction? AlX3 acts as catalyst. What are the points here? First one, what is the electrophile in this step in Friedel-Crafts alkylation reaction? Alkyl carbocation or alkyl carbonium ion. You can also call anything. Is the electrophile, acts as electrophile. In Friedel-Crafts alkylation reaction, anhydrous AlCl3 or AlX3, Lewis acid, acts as catalyst. So in the place of anhydrous AlX3 we can also write Lewis acid. Lewis acid acts as catalyst. Then what is the intermediate in this reaction? Sigma complex. Sigma complex is the intermediate. What is that? Intermediate. So once again we can write reaction. For example, benzene on treating with Rx in the presence of anhydrous Lewis acid AlX3. So what happens here? Here also hydrogen is there, everywhere we can take. H is replaced by R group. Alkyl benzene plus HX plus AlX3 is there, so no need to write that one. Then, so we'll see the applications. In the place of R means what? Alkyl group. In the place of R, methyl group, ethyl group, isopropyl group, anything we can take. So we'll see some specific examples. Benzene on treating with methyl chloride in presence of anhydrous AlCl3 I am taking, X3. Here chlorine I have mentioned, chlorine I am taking. Not only that one, you can take Br also. So one hydrogen is replaced by alkyl group. Which alkyl group is there here? CS3 group is there. So hydrogen is replaced by methyl group, CS3. That hydrogen will combine with whom? Chlorine. So this is nothing but toluene, also called methyl benzene. One more example. Benzene on treating with ethyl chloride, C2H5Cl, or ethyl bromide. I am taking CS3, CH2Br. Anhydrous AlCl3, anhydrous FeBr3. So what happens here? That is also Lewis acid only. Hydrogen is replaced by ethyl group. So hydrogen is replaced by ethyl group. So what is the electrophile here? Two carbons are there here. Electrophile formation I am writing. Then CS3, CH2, Br. On treating with FeBr3 anhydrous. This is also Lewis acid. FeBr3 take electron pair from the bromine. Between the bromine and iron bond formation takes place. Bromine gets positive charge. It take electron pair from this. Which gets positive charge? This one. CH3. Two carbons are there. In that CH2 carbon gets positive charge. FeBr4 minus will be formed. So this acts as electrophile. What is the name of this one? Ethyl carbonium ion. Ethyl carbonium ion. Also called ethyl carbocation. So this is electrophile. Now here, what is the main important thing? Many students will write like this. Is this correct? This is 100% wrong. Why? In the alkyl carbocation, ethyl carbocation, two carbons are there. Out of those two carbon, one carbon is having charge, is nothing but positive charge. So which is electron deficient carbon? This carbon is electron deficient carbon. That carbon, electron deficient carbon only required electrons. It is taking electron pair from the benzene ring. So this carbon should be connected to benzene ring, CH2, CH3. So what is the name of this one? Ethyl benzene. We'll see some more examples. That is fine. Ethyl group, ethyl benzene. Methyl group, methyl chloride, methyl benzene is formed. I am taking one more example. Benzene. On treating with CH3, CH2, CH2Cl or Br or iodine. Then on treating with anhydrous AlCl3. So what is the product here? So we can understand and we can easily write the product based on the electrophile formation step. So I'll give the electrophile formation step here. CH3, CH2, N-propyl chloride. What is the name of this one? N-propyl chloride. Is going to react with Lewis acid, is nothing but AlCl3. Lewis acid is electron pair acceptor, electron deficient. Electron deficient species required electrons. It can take electron pair from the halogen because of having lone pair of electrons. That halogen gets positive charge, it take electron pair from this one. Then electrophile will be formed CH3, CH, hydrogen and CH2 plus. Of course, this one I can also represent CH3, CH2, CH2 plus. This I can represent. I represented in this way. Both are same only. Why I have represented? Here electrophile is formed. Carbocation, that is nothing but carbocation. What type of carbocation? Primary carbocation. In electron displacement effects, I discussed about the stability of the carbocation. Which carbocation is more stable? Tertiary. But here primary is formed. After formation of the primary carbocation, we can easily check, is there any possibility to get the more stable carbocation than the formed carbocation by rearrangement. If hydrogen migration takes place, H minus migration, of course, hydrogen migration is taking place, we don't observe, but this is for explanation. Then H minus, hydrogen shift, H minus shift. Why? Stability. This is stability factor. CH3, CH plus, CH2 plus and H minus, CH3. It becomes CH3. So, what type of carbocation is formed here? Secondary carbocation is formed. In this case, only two types of carbocatons are possible. One is the primary carbocation, another one is the secondary carbocation. Out of these two carbocatons, which carbocation is more stable? Secondary carbocation is more stable. So that's the reason this is a stable electrophile. So that electrophile can react with this one. Electrophile is going to react with benzene ring. So that means what? Hydrogen is replaced by this secondary carbocation, isopropyl carbocation. So what is the product here? Benzene. Out of those 3 carbons, which carbon has to react with the benzene ring? Which carbon is going to connect? This carbon, middle carbon, CH. CH3 and CH3. So what is the name of this one? Isopropyl benzene. Isopropyl benzene. This one you can also call cumene. General name is cumene. Then one more example. Some more examples we'll see. Benzene. On treating with cyclohexyl bromide or cyclohexyl chloride. This on treating with N-hydrous AlCl3. So what is the product? Here hydrogen is there. Everywhere hydrogen is there. Hydrogen is replaced by alkyl group. Which is the alkyl group here? Cyclohexyl group is acting as alkyl group. Cyclohexyl chloride or chlorocyclohexane is the IUPAC name. So cyclohexyl ring is connected to whom? Benzene ring. Cyclohexyl group is connected to whom? Benzene ring. Cyclohexyl benzene is the product. Then one more example. We'll see here. I'll give you an example. You can try. Benzene. On treating with alkyl halide I have taken. Which alkyl halide? Here which ring is there? Cyclopentyl ring is there. Is connected to CH2 group and chlorine. Okay. Cyclopentyl chloromethane. 1 chloro, cyclo, Cy, chloro, CH. Which one do you have to write? Chloro, cyclopentyl methane. On treating with N-hydrous AlCl3. What is the product? This is the most important thing. Then we'll see. Mechanism. Alkyl halide on treating with N-hydrous AlCl3 is acting as Lewis acid. It can take electron pair from the halogen. Between the halogen and aluminum bond formation takes place, and again chlorine gets positive charge. It take electron pair from this one. Cyclopentyl methyl carbocation, CH2 plus. Then carbocation is formed. What is the next step? After formation of the carbocation, we have to check, is there any is that more stable carbocation or any other possibility is there? This is not stable carbocation because ring adjacent carbon is having positive charge. Given ring is 5-membered ring. So generally 6-membered ring is more stable than the 5-membered. 5-membered ring is the more stable than 4-membered. That is explained based on the heat of hydrogenation. Then here ring expansion takes place. Carbocation carbon, adjacent carbon is alpha carbon and adjacent of alpha is beta. This one also beta. Already I gave you how do we have to do the ring expansions and ring contractions. I am directly writing here. So between the alpha and beta carbon, ring is expanding. How? Ring is expanding. Alpha, beta, ring is expanding. That means here cyclopentyl this bond is there from here to here. This is the bond, it is shifting like this. This bond is there, here it is shifting like this. This carbon between the alpha and beta connectivity has lost. That's why the alpha carbon gets which charge? Positive charge. So which member ring this one? 6 carbons are there. One carbon is having positive charge, this one. So that is primary carbocation, this is secondary carbocation. Not only that one, that is 5 membered ring. Previously this is 6 membered ring. Which is more stable? This one, stable carbocation, stable electrophile. So now what is the product here? Stable electrophile can react with whom? Benzene ring. Stable electrophile can react with benzene ring. So what is the product here? Benzene is connected to cyclohexyl carbocation. Cyclohexyl benzene. This is acting as cyclohexyl group. Is connected to benzene, cyclohexyl benzene. Done. So not only this, so many examples we can explain. Under 2 more examples I'll give you. We'll see. Two more examples I'll give you here, and we'll go for the other applications. Substituted benzene applications also we can do. Benzene. On treating with isobutyl bromide. On treating with anhydrous Lewis acid, FeBr3, iron, whatever it is, iron also they may give. So what is the product here? Benzene is going to react with whom? Of course, HCl, HBr, those are the byproducts. But main product is what? Benzene is going to connect with whom? Which carbon? We can understand based on first step. I am not writing second and third step because both are same only. Isobutyl bromide, CS3, CH, CH2Br. 1 bromo 2 methyl propane also we can call. Isobutyl bromide. On treating with anhydrous FeBr3, bromine is having lone pair of electrons. It can take electron pair from that. Bromine gets with charge, positive charge. It can take CH3, CH3. Here, this hydrogen I am representing like this for rearrangement purpose. CH2 plus and FeBr4 minus. Then, this is what type of carbocation? Primary carbocation. Which is the more stable carbocation? More stable is tertiary, than secondary, than primary. Then, is there any possibility to get the more stable carbocation by rearrangement? Yes, 100% rearrangement is possible. Hydrogen migration takes place. H minus is migrating. So, what is the product here? CH3, CH3, hydrogen carbon gets positive charge. H minus is connected to CH2 plus, is becoming CH3. So what is the name of this one? Tertiary carbocation. What is that? Tertiary carbocation. So this is stable carbocation. Stable carbocation, stable electrophile. So it can react with whom? Benzene ring. So this carbon, middle carbon is attached to benzene ring. Then is connected to CH3, CH3 and CH3. Tertiary butyl benzene. Tertiary butyl benzene is the product. Then some more examples we'll see. Benzene. On treating with vinyl bromide. This means this is alkynyl bromide. Anhydrous FeBr3. Anhydrous. So what is the product here? So generally, what is the electrophile? Halide ion elimination takes place with Lewis acid. Alkyl carbocation will be formed. But what about this one? In this case, whenever you observe this one, H2C double bond, CHBr, bromine is having lone pair of electrons. Lone pair of electrons are conjugation with double bond group. So that's why we can't break the bond between the double bond carbon and bromine. So because of conjugation, partial double bond character is developed between the carbon and bromine. That's why electrophile formation is very difficult. That's why this reaction is not possible. Okay, not possible. One more example. Then how can we explain, is it possible or not? We have to form the stable carbocation. If stable carbocation is not possible, reaction is not possible. Benzene, on treating with halobenzene, fluorobenzene, chlorobenzene, bromobenzene, whatever it is. On treating with anhydrous Lewis acid, AlCl3, X3. So what is the product in this case? Is this forming phenylbenzene or diphenyl? Is it forming? Then halide should eliminate this as to get the positive charge. So positive charge means what? It has to react with the benzene ring. This should be formed, but reaction is not possible. Reaction is not possible. Why reaction is not possible in this case? Because whenever we take halobenzene, halogen lone pair of electrons are conjugation with benzene ring. So that means double bond character is developed between the benzene carbon and halogen. That's why we can't break the bond between the benzene and halogen. That's why here also no reaction. Here also no reaction. Okay. Then one more last example with benzene ring. I'll give you one more example. Benzene on treating with benzyl chloride. In presence of anhydrous AlCl3. So what is the product here? Then, so we can understand based on the electrophile formation only. Benzyl chloride, CH2Cl. Do you have any doubt? CH2Cl I have written here, but now I am taking right side. Both are same only. Only one substituent is there. On treating with AlCl3, halogen is having lone pair. It can donate electron pair to the aluminum. Halogen gets positive charge. It take electron pair from CH2. CH2 plus will be formed. CH2 plus. But previously, whenever we observe this reaction, then benzene has to get the positive charge. Erinium ion is unstable. That's the electrophile formation is not possible. But in this case, benzyl carbocation is electrophile. Benzyl carbocation, electrophile. Which electrophile? Stable electrophile. So stable electrophile is possible. Why? Benzyl carbocation is more stable because of resonance. So electrophile formation is easy. That's why benzene ring should be connected to whom? I'll write the product here. Benzene ring I am writing here. Benzene is there. It is connected to CH2 group. The CH2 is connected to one more benzene ring. Diphenyl methane type. That is the product. This is about Friedel-Crafts alkylation reaction. Okay, in next class, we'll discuss about the applications of Friedel-Crafts alkylation, substituted benzene applications. Okay, thank you.